factors that affect resistance को complete कर लिया था हमने? We did numericals also. First we'll complete it, then we'll analyze. Huh? Yes, we did. Yes, what and what. So we had completed till factors that affect resistance. So what are the factors that affect resistance? There are 4, right? What are they? So it changes with the length. If the length of the conductor is doubled, resistance will be doubled. What about thickness or area of cross section? There is an inverse relation. Third, it also increases with temperature, right? It increases with temperature. Fourth, or changes with area. Nature of nature of yes, so we are done till here. Did we discuss resistivity? Huh? We have not discussed resistivity. So we have discussed till here. So from 1 and 2. There is a resistance of a conductor changes with the area of its diameter. Therefore, resistance is not the characteristic of. Very close. So how many of you have not attended from the beginning? This year? When I started current electricity, who all were present? Raise your hand. Very few were present. So we have covered till here. So you want to see the video lecture, and if you need any assistance, then you need to ask. We haven't covered much till here. What we have done till here is we have actually defined what is current. I'll just write here what we have done till here. Electric current. So, I. What is electric current? Defined as rate of flow of current. So those who did not attend, pay attention. The first topic is electric current, which is defined as rate of flow of charge. And what is charge? N times E. How the charge is made? It is made by the number of electrons. N is integer, and E is charge of 1 electron. What is charge of 1 electron? 1.6 into 10 raised to -19 coulomb. So E is this. The charge of electron is -E. But since I is the conventional current, and conventional current is due to positive charge. Okay, that's why we are taking ES plus 1.6. Then we covered Ohm's law. The second topic we covered was Ohm's law, which gives the relation between the potential difference applied across the conductor and the current flowing through the conductor. So Ohm's law states that there is a direct proportionality between the applied potential difference and the current flowing through the conductor. Okay? So there is a direct relation. What does it mean? If you increase the applied potential difference, it will increase the current in the same proportion. Okay? So this is what is called as Ohm's law. When is it valid? When the temperature is constant. This law is valid only for constant temperature. So at constant temperature. Okay. Now when you remove the proportionality, what you get is R. So R is called resistance. So R is a constant where R is constant called resistance. So whose resistance? Resistance of the okay, so this is your Ohm's law. Then all the devices that obey Ohm's law are called ohmic devices. Okay, all the devices that obey Ohm's law are called ohmic devices. Likewise, those who do not obey Ohm's law are called non-ohmic devices. Okay, as simple as that. If ohmic devices obey Ohm's law, non-ohmic devices they are not obey Ohm's law. Non-ohmic device does not obey Ohm's law. What is the meaning of obey or do not obey? Like if in a non-ohmic device, if I increase voltage, the current will not increase in the same proportion. So you will not get a straight line. So if you draw a VI graph for this, a VI graph should be a straight line. For an ohmic device, the VI graph should be straight line. For a non-ohmic device, it can be anything but a straight line. Okay, so the second graph is graph for non-ohmic device. It could be anything. The curve could be in any direction. As long as it is a straight line, it is a ohmic device. Is that clear? So this is what it is. So we said R is a constant for resistance of the conductor, and how it is measured? It is measured in what is the unit of resistance? Unit is ohm. Unit of resistance is ohm, and its symbol is this omega, Greek letter omega, capital. Okay? That's called ohm. So now we went forward. We then studied the property of resistance. So what is resistance basically? To resist means to oppose. So resistance basically opposes the flow of current. Whenever the electron moves through the conductor, its motion is not free flowing. It is always obstructed by the stationary positive charges. Okay? So it collides with the stationary positive charges. And that obstruction, the measure of that obstruction is called resistance. Is that clear? So higher the resistance, less and less current will flow through the conductor. Okay? So what does that resistance depend? So obviously, if the length of the conductor is doubled, right? So resistance will increase only. Because earlier the obstruction was only in this much length. Now when the length increases, the obstruction also doubles. So resistance will double. There is a direct proportionality. If the thickness of the conductor or area of cross section is doubled, so it has more room to navigate. Like if I have a passage, so if I make it more wide, so now there will be less obstruction to the movement. Okay, just like that. So when the area of cross section of conductor is increased, the resistance has to decrease. That's why it is inversely proportional to area of cross section. Now, when the temperature of the conductor is increased, so these stationary positive charges, they will begin to vibrate. They will not leave their position because they are not mobile. The positive stationary charges are fixed. Only the free electron in the valence shell that moves throughout the conductor. Okay. So when the temperature rises, those positive charges begin to vibrate, and then the movement of electron is obstructed more. It's like when I'm trying to walk, and you putting your legs in between. Okay, so that will increase the obstruction. So this is what happens in this case. So with temperature also the obstruction increases. So see the obstruction as collisions. Collision of electron with the stationary charges, stationary positive charges. Then fourth is also resistance will change when you change the substance. Like from copper, if you take aluminium, then the resistance will be different. For copper, it is less. For aluminium, it will be slightly more. For silver, it is less than copper. Okay. So when you change the material, so by the nature, by the composition of the material, the obstruction to the flow of electron is more or less. So more the number of availability of free electron, more easy for the current conduction. Is that clear? So there is the fourth option. So now we want to remove the dependency on length and area of cross section. Even if the material is same, let's say copper, if you change the length of the conductor, then its resistance changes. So therefore, resistance is not a correct characteristic constant for a given material. It changes with the dimension. So therefore, if you combine 1 and 2, what do we get? We get this. So when we remove this, so we get a constant of proportionality called rho. It is called resistivity or specific resistance. What is rho? Where rho is called resistivity or specific resistance. Yeah. So what is the specific resistance now? RA by. Now, what is the unit of rho? Unit of resistance is ohm, meter square per meter. So ohm meter. Okay? Unit will be ohm meter. So how do we define this resistivity? You see, if L is equal to 1 unit and A is also equal to 1 unit, then numerically rho is equal to R. Correct? So how do we define resistivity then? Resistivity is nothing but resistance of the conductor of unit length and unit area of cross section. So resistivity is also resistance, but for a specific conductor whose length is 1 meter and whose area of cross section is 1 meter square. So now we have frozen the dimension. We have removed the dependency of length and area from resistivity. Okay. So therefore, what is resistivity? Yes. It's resistance. Okay. Okay, this is how we define resistivity. So now what are the factors on which resistivity will depend now? It will only depend on the temperature and material. So the dependency on dimensions is gone. Okay? So resistivity, factors that affect resistivity. Temperature. Since in this chapter, we are only going to discuss the cases of Ohm's law. And Ohm's law is valid for only constant temperature. So now we have removed the dependency on temperature also. Okay? So resistivity will only change with the material. So if you look at your book, okay, you probably have the table that shows resistivity of various materials, conductors of various materials. Okay. So on the basis of resistivity, the materials are classified as conductor, insulators, or semiconductors. So resistivity should be low for conductors, obviously. Right? Conductors are path for the current to flow. Right? So conductor should have least resistivity. Insulator should have maximum because we don't want the current to flow through insulators. Okay. So that's why if you cut this wire, right, if you peel off the insulation, then you will have copper wire. So the current flows through the copper wire and you have protected it from outside with the help of insulator so that when you're handling the wire, it doesn't give you a shock. So current does not reach your body because we are also conductor. The current can flow through our body. Okay. So human body is also a conductor. Then you can see insulator, wood, glass, etc. The resistivity is very high. You can compare it for yourself. Is that clear? Yes. So on the basis of resistivity, substances can be classified as insular. So in conductors, they have least resistivity. Semiconductors have moderate resistivity. And they have high resistivity. Among conductor, you also use alloys. Alloys are mixtures of conductor, like nichrome, manganese. These are alloys. So alloys will be placed here. Alloys are made up of mixture of different substances. So sometimes to control current, we do require resistance. Okay, like fan speed. So if you want to increase the speed of the fan, do we need to pass more current or less current? So to increase the speed, I have to select a resistance of low value. So here you see 1, 2, 3, 4 speeds are there. So when I'm going from say high speed to low speed, I'm actually increasing the resistance. When I'm going from low speed to high speed, I'm decreasing the resistance. Okay, so basically there are different resistances. So when you turn the knob, different resistances connected. Okay, so you have like, let's say these are 3 resistances. So when I put the knob from 0 to here, so it is on the highest value of resistance, so low speed. Then when I switch, now this is connected. This is connected. So circuit is completed through different resistors. This is how it happens. Okay, is that clear? Okay, now you can read the difference between ohmic conductor and non-ohmic conductor yourself. Read the difference between ohmic conductor and non-ohmic conductor. Discussed the law, Ohm's law and its VI graph in the last class. VI graph is discussed. Only superconductor is remaining here. And also how we choose choice of material. Application. So depending on the application, the suitable material is chosen. For example, if I want to use as connecting wires, so what kind of material I should choose, with high resistivity or low resistivity? Low, because that fan is the device and I want to connect it to the source. So then I will use this kind of wire. These are conducting wires or connecting wires. They should have very, very low resistance. Whatever, when the moment I switch on the supply, current should immediately reset with least resistance. Okay, no energy should be consumed inside this. Okay, all the energy should be consumed by appliance. So connecting wire, so would have low resistance. Low resistance. So what kind of wire should I choose? So you can see the table: copper, copper or aluminum. Okay, but mostly we use aluminum for transmission cable outside, you know. But in house we use copper. Do we use aluminum? Sorry, do we use silver? No, silver has least resistivity, but it's expensive, so we don't use it. Then, if I have to use heating element, so heating element, what do we use here? Here we use heating element. Mein we require high resistance. Okay, so we use alloy. So alloy mein we use nichrome wire. So nichrome is the alloy of nickel, chromium, and I guess copper. Nickel, chromium, copper, or nickel, chromium, iron. Okay, so you can check on Google what is the alloy, what is the metal mixture of nichrome. So individual metals have low resistivity, but when you mix them, their resistivity increases. So then they are more suitable for high resistance application, such as in heating element. So when you are using an electric iron, so electric iron would require what? A heating element. Inside there is a heating coil. So when you pass the current, it becomes hot. Okay, or a heater or a geyser. Okay. Generally, heating coils are made up of nichrome. Then, so if it is filament of bulb, what do we use in the filament of bulb? Tungsten. Okay, so you use tungsten. Tungsten. So heating a nichrome, it has high resistivity. High value of. What about filament of bulb? Obviously, it will have high resistivity as well as very high melting point. So high, very high melting point. Because when the bulb filament glows, right, it becomes heated and then it begins to glow, right? But it should not melt. It should keep glowing and giving us light. Okay? तो इसलिए इसका जो melting point है बहुत high. Any idea what's the melting point? Almost 4,000 Celsius, almost 3,080 or something. Just check, it might be given. Everybody knows what a 100 degrees Celsius boiling water feels like. The temperature of a boiling water is too much. We are talking about 4,000 degrees centigrade. Okay, so how many times? 40 times more. And it still stands. So you may know what is the temperature bearing strength? What else? Fuse wire. So we are going to study it in more detail in the next chapter. So everybody has heard about fuse. Heard about fuse wire or fuse? Fuse उड़ गया बोलते हैं तो क्या होता है? Bad हो जाता है. तो fuse wire क्या होता है? Like when you connect any device, right? So every device, every expensive device will have a fuse also inside it. So fuse में क्या होता है कि let's say, or you'll understand it in the next chapter more. When these wires, they always run in pair, live and neutral. So the live is at higher potential, current enters the circuit through the live wire and it returns the source of supply through the neutral wire. Sometimes what happens, these live and neutral accidentally come in contact with each other. Actually, what should happen? Live wire and the appliance is connected and then the return should be the other end. But these wires run together, but they are insulated. But over a period of time, due to wear and tear and due to wear and tear caused by harsh weather, the insulation peels off and live and neutral come in contact before entering the appliance. So appliance is out now and live and neutral have come in contact, so there is zero resistance. So when there is zero resistance, what will be the current? Current is V by R, V by 0. Very high current will flow. Okay? Accidental coming in contact of live and neutral is called short circuit. You must have heard in the news that fire outbreak took place in an old building due to short circuit. This is the reason. The live and neutral come in contact accidentally due to peeling off of insulation. This. That's why you should replace, one should replace the wires after 10 to 15 years. That's the life. At least after 10 years. Okay, so short circuit में क्या हो गया? When high current flows, a very high, the conductor becomes very hot. And copper has very high melting point. And it is running through wood, etc. Right? So if it crosses the ignition temperature of the wood, this will catch fire. Okay? So before that, in the conductor, what we connect is fuse. The fuse wire has low melting point. So conductor, copper wire has high melting point, but the fuse wire has low melting point. So it is connected in between somewhere. So the moment high current flows, the fuse wire melts. The fuse wire melts and it breaks the circuit. Okay? So it saves you from fire outbreak. So it's a safety measure. So generally, it is an alloy of lead and tin. Okay? It has high resistivity and low melting point. Okay, it is safety measure against short circuit. Overload. So there are two reasons for high current flowing in the circuit. One is short circuit, like accidental coming in contact of live and neutral. The other is overload. Overloading means your wiring is adequate only to carry a current of say 5 amperes. And you connected a load, say air conditioner to that wire, which requires 10 ampere minimum. So wire is designed for carrying a load of 5 ampere. And you are pulling 10 ampere from it. So that will become hot and it may burn out. Or it may catch fire also. Okay. So this is, so therefore fuse, if there is fuse connected, it will basically break the circuit. So that will come to know, right? Today, instead of fuse, we use what is called as MCB. What is it? MCB. MCB is basically miniature circuit breaker. So whenever there is an overload, right, or short circuit, when excess current, more current than normal current is flowing, there will be this is a mechanical switch, it will trip. Okay, it will break the circuit. Again, if you try to switch on it, it will again trip. Till the problem is fixed, it will keep tripping. So basically by tripping, it will save the fire outbreak. So tripping is the indication that something is wrong with your electrical network. So time to call the electrician so that he can investigate what's the problem. Once he fixes the problem, then we can switch it on again. So how it is different than the fuses? Here you have to, once the wire is melted, you have to replace it. So some fixing is required. But here after the problem is fixed, as simple as just switch it on. Okay. So obviously this is expensive and so both are used as well as it's. Okay. And this is the topic of the next chapter. So we'll move on now. Next is superconductors. So how are we classifying materials on the basis of their application? Now what is this? This is a superconductor. So what about its resistivity? 0, correct? It has no resistance, 0 resistivity. So if the conductor has 0 resistivity, will it consume energy? Where is energy consumed? In overcoming obstruction. So when there is no obstruction, there will be hardly any energy consumed. So if you switch on any appliance which is running on a superconductor, so there will be no energy loss or minimal energy loss. Okay. But unfortunately, we don't have any superconductor that works at ambient temperature. Superconductors have been tested in laboratory at sub-zero temperature, around 4 Kelvin, etc. Okay, 4 to 10, 9 Kelvin, that range. So we can't use it for our daily usage as of now. So still people are, researching on having materials which can actually act as a superconductor at room temperature. As on date, it is not possible. Okay. So imagine if we have superconductors, then we can have those maglev trains. Have you heard about maglev? Magnetic levitation. So when the train runs on the track, it is not in physical contact. It is suspended by a few inches. But today they do it with high strength magnetic fields. Opposing magnetic fields are generated between the tracks and the train. So the train floats above the track. So there is no friction, but it consumes a lot of electricity. So if we have superconductors possible, then we'll save a lot of cost and high mode of transportation. Okay. So that's about superconductors. Some example of superconductors are mercury, right? Mercury behaves as superconductor at around 4 Kelvin. In your book, you will see the example. It's not mentioned here. So 0 will be like ideal. Okay, you say almost 0. Okay, near 0. Okay, the near 0 range की है. मैं तो उसको अमर हो जाए. ऐसा नहीं हो सकता. Okay. So there is the last point here. Resistance and resistivity remain unchanged for alloys with increasing temperature. So let's say you have this television. Okay. Now in a day, what is the temperature variation from morning till evening? You might be seeing those weather forecasts, minimum temperature, maximum temperature for the day. The temperature variation is about 4-5 degrees in a day, right? So does the TV behavior changes during that temperature fluctuation? No. So the resistance of the material used in the TV is like it is not dependent on such a small temperature variation. It is not affected. So such kind of tolerance is required. Okay. Otherwise, all our devices will start acting funny with little bit of change of temperature. Right. So that tolerance will have to be built. Right. So it remains a ohmic device for this much range of temperature. Okay. So the more the temperature range the material can handle, the better. Then we can use it in desert conditions also, because in India, the temperature fluctuation is within 5 to 10 degrees Celsius. But in desert, the temperature gradient is more than 20-30 degrees in a day. Morning, evening temperature, but there also the devices keep working okay. And in a military grade environment, we need to select material which can handle even bigger temperature range without changing the resistance. Okay. So in the last line, we have resistance and resistivity remain unchanged for alloys. So alloys are like less temperature dependent. So they can handle larger temperature variation. Right? For semiconductors, resistance decreases with increasing temperature. Now semiconductor is, so far we studied when we increase the temperature, resistance increases. But for semiconductor, it is the other way around. When you increase the temperature, its resistance decreases. Okay? But more about that in 12th standard. So semiconductor is what kind of device? Ohmic or non-ohmic? Huh? Non-ohmic. Semiconductor device is non-ohmic. Okay? And what about this alloy? Its resistance is not changing with temperature. So R is constant. So this would be ohmic device. Okay? Wherever Vi slope is constant, slope itself is resistance. Wherever Vi graph is constant, it is ohmic device. So with this, we have completed the first part. Okay. Let me ask you some questions. This is a VI graph for three conductors. ABC. ABC are three conductors. Okay. So first of all, identify which is ohmic and which is non-ohmic. Huh? B and C are ohmic. And this is non-ohmic. Which is most suitable to be used as connecting wire? Huh? C has high resistance or low resistance? Look at the slope. Low resistance. What is resistance? Slope, no? Slope of VI graph gives you resistance. Whose slope is high, C or B? C has high resistance. Is it suitable to be used as conductor? Not. Okay. So, okay, you can use B as connecting wires. So this can be used as a resistor. Okay. Or a heater. Okay. Now the other question is like this. Okay, let me. Which conductor has high resistance? A or B? Huh? Somebody is saying B, somebody is saying A. Which conductor has high resistance? A. How many with A? A is wrong. What is the graph? EI or IV? This is how they will twist. So now what is resistance? 1 by R. Okay. So just don't. So this is the disguise. This is how they will twist the question. So it's not that always higher slope means high resistance. It depends whether it is IV graph or EI graph. So what is the slope here? Slope in this case is reciprocal of R. So less slope will mean high resistance. Less slope will mean high resistance. So this has high resistance. B has high resistance, less slope. Is that clear? So B is correct in this case. Now one last question on this. So these graphical questions are logical. You just like many of you get scared just by looking at the diagram. Generally, diagram questions are very easy. It is based on logic. Okay, but then they will make your life little difficult by twisting it. Okay. So आप देखो इसमें it is the graph of the same conductor at two different temperatures. What is the graph about? Graph of the same conductor at two different temperatures. Identify which is the greater temperature. What is the greater temperature? T1 or T2? T1 has to be greater. Why? R is proportional to T. So higher temperature should have higher resistance. In this case, which is high resistance? Bigger slope. T1. Understood? So in this case, T1 is greater than T2. Okay, so these are some of the questions that may be asked. Okay. So what is the example of? Look at this question, example 8.6, 33, page 33. Everybody go to example 8.6, 33. Volume लेके आएगा वो. So that at least we have one common resource. Is everybody comfortable? Is the question understood? So it's nothing different than what we have done. Now we move on to the next one. EMF. Next is EMF. Let us understand what is EMF. Full form is electromotive force. So what is EMF? EMF is, let's say if you have a cell, in a cell, EMF is the potential difference between the terminals of the cell when no current is drawn from it. But when cell is not used, then the total potential difference between the terminals of the cell is EMF. Okay? So this is EMF. EMF is the potential difference. Okay? EMF is the potential difference between the terminals of the cell when it is not in use. That is when no current is drawn from it. Okay? No current is drawn from it. This is how it is defined. So to understand it more better, let us say we have a circuit diagram. So this is a typical circuit diagram that we will come across often. There is one more definition for EMF, because what is EMF? It is the potential difference. And what is potential difference? How did we define potential difference? Work done per unit charge. Okay. So in terms of work done, EMF is the work done in taking the unit positive charge through the full circuit. Okay. What is the full circuit? Full circuit is, now this whole thing is cell. The dotted box is cell. So it has its own resistance also. Cell has electrolyte. Okay. Now electrolyte is also conducting medium. So it will also have its resistance. There will be some obstruction within the cell also. So R is the internal resistance of the cell. Okay. So if I call this as point A and point B, everything outside AB is external circuit. And everything inside AB is internal circuit. Okay. So what is EMF? It is work done in taking the unit positive charge from A to A, full circuit. Okay. So EMF is also defined. As work done. Then okay. Very good. So, what is external circuit? Outside the cell. What is internal circuit? Inside the cell. So from A to A to B is external circuit. And A to A, and only B to A is internal, but A to A is full circuit. Is that clear? So A to A is full circuit, A to B is external, and B to A is internal. Okay. So if I have to write it in terms of expression, therefore, what is the work done per unit charge? Okay. So this is equation form. So we'll resume it in the next class.